I'm going to talk about causal inference. It's going to be a very a brief introduction about the topic. I will also try to give you a few pointers about more advanced tools that we have in the field. But I hope that you enjoy. And of course, if you have any interest in the field, I'll be happy to talk more after the lecture. You can even contact me through my email and so on. So I will start about comparing. So most of the tools that we have been using in machine learning are focused on having or making predictions. So they are like predictive models, and we are trying to move towards what is more what is explainable or trustworthy AI. So what is the difference between these two models? So we have, for example, systems, right, that are now better than human doctors at predicting disease, breast cancer, for example. So we can do prediction pretty well. However, how can we explain how the outcome is coming about, right? What is the reasoning behind these algorithms? So we can also learn from the algorithms to do the same. We don't know, we don't have like today we don't have a good technique to do this yet. Fairness is something related to explainability, because since you don't know how are the outcomes coming about, you don't know if it's using some sensitive variables and are being fair according to the standards of our society. Another example is like ChatGPT. So we have a lot of tools that we can do a lot of tasks with ChatGPT. Is very impressive. However, this classic answer engine is still outmarks AI chatbots, which means that sometimes even something very classical are still better than this than ChatGPT. For example, this is another example. GPT-4 still can't reason, but it's phenomenally useful tool anymore. So the first news is more about like calculations. I don't know if you can read here in the top here. For questions involving hard data and math calculations, 15-year-old Wolfram Alpha is a fast, accurate alternative to inaccurate AI chatbots. So this means that reasoning is still really hard to do when you are trying to just make predictions. We need something more, and I'm arguing here that causality is one of the missing link to reasoning in AI. So the ability to understand causal effect relationships is crucial for deeper understanding and decision-making process. So we have this news also in Nature that says that a machine with a grasp of cause and effect could learn more like a human through imagination and regret. So we are missing this ability of distinguishing between simple associations, simple statistical associations that are basically all we need for prediction. We need to move towards what it's more towards a causal and effect relationship. So let's try to understand what is this difference. What's the difference between prediction and effect of interventions or causal effects? So imagine here that I have this task. So can I guess how severe is a fire just by observing the number of firefighters? So you look at the window, you see a lot of firefighters there. And can you guess how severe is the fire out there just by looking that you have maybe 100 firefighters out there? What do you think? It's a very, very big fire, right? And yes, you can guess. You're doing a prediction task here. So we can get, for example, the number of, like we have two variables, X and Y. We can then do any type of try to estimate the statistical association between them, for example, a regression analysis, and we'll see, for example, in this simulated data, I have here, so I have an R-square of 92, which means that's explaining pretty well the observed data. So correlation tells me that the correlation between X and Y tells me that the X variable, or the number of firefighters, is a good predictor of the task, of the severity of the fire out there, right? So this distribution is usually called observational distribution. So this is basically definition of what's the of statistical association, right? So if you have here that after observing the variable X, we have a probability, so the conditional probability. So given that I know the variable X, what would be the probability of Y? If this probability is different than the marginal probability of Y, this means that X is actually helpful in my prediction, right? So this difference tells me what I can do or not regarding to predictive tasks. So, okay, we have this very simple analysis, and we can conclude that the severity of the fire increases with the number of firefighters, okay? So, can I use this to do decision making? So what is the reasoning now behind? So now I'm changing the task. So I know from before that the severity of the fire increases with the number of firefighters. So the fewer firefighters, the weaker the fire. Maybe you are already guessing what's basically the catch here. So can I do this jump? Should we decrease the number of firefighters than to reduce the fire? Now it's a decision-making process, right? So it's different. And what do you think? Should I decrease the number of firefighters to reduce the fire? Obviously not, right? So this is like a very silly example, but many times we do this in research. We try to extrapolate from what we observe as a statistical association to say that this is by saying that a variable is a good predictor, this means that changing the value of this variable, you help in the sense that making a change on the variable that a predictor, you expect also a change in the outcome. Imagine that I observe that a gene is associated to a disease. People are going to try to develop a genetic treatment to change this gene to cure a disease. But this doesn't mean anything. It's exactly the same analogy that I'm doing here. It can be something that's confounded with this gene and is creating a spurious association. So knowing that knowing that a variable is a good predictor doesn't mean that you can act on this variable and expect a change in the outcome. And decision-making requires this knowledge, requires cause and effect relationship, requires that the variable that's a predictor is a cause to then expect an effect in the outcome. Okay, so that's basically the conclusion. So causal effect is just, usually when I say here about causal effect, is a quantity that's going to tell us how much Y, or the outcome variable, changes of an intervention. And in the field, we have a notation for intervention, so this doesn't mean that we actually intervene on the variable in reality, it's just a hypothetical intervention, but we have a mathematical notation for this hypothetical intervention that's called do. The do operator means I'm changing the variable X to have this small x here, okay? And any quantity that's related to this is going to be called causal effect. So it could be, for example, the expectation of Y given that I had this intervention on X. So for example, if a different number of firefighters were dispatched, right? So now we changed X to be a different X. X is the number of firefighters. Would this change the expected severity of the initial fire? So now we are asking in a more formal way the same question that I had before, which is about, if I intervene or if I change the number of firefighters, what is the expected change in my variable Y, which is the severity of the fire? So in this case, it won't change nothing, right? Of course, the fire's already there. So there is a matter of temporal relationship going on here. But this would answer what would be the causal effect of this intervention. So this quantity is derived, for example, so we need the probability, and we will call this probability. So the quantity, the causal effect, could be the expectation, requires the probability. And this probability is not the observed probability distribution that we are used to. We are now have this notation for the distribution of a set of variables. In this case, it's just the variable y, but conditioned on the fact that I performed this intervention. So it's like another reality. It's a different reality. And I don't necessarily have the intervention, but I want to know what would happen in the case that I had this intervention on X. And this is commonly referred as interventional distribution. Okay? So the question about causal effect, or how can I infer this interventional distribution, can be answered today through several techniques. Can someone here tell me one of the techniques used to infer causal effects? So if I ask you, I need a causal effect of something, like a drug, if I want to know if the drug has a causal effect or a positive effect in curing a certain disease, what do you think people are used to do right now?
Like a randomized control trial?
Exactly. So that's the standard today of how to infer effects of interventions or causal effects. And why this works. I'm not sure if this is the slide that I will talk about this, but let's just, I think it's the next slide. But here, basically, I would need to answer the question, I would need some type of knowledge about how the variables are related to each other. So imagine that I have this set of functions, right? So I have here the two variables. This is the same example as before, X and Y, X being the number of firefighters, Y being the severity of the fire. And I know that the number of firefighters depend on the severity of the fire, not the other way around, right? So you dispatch the number of firefighters according to the severity of fire. And you see that the fact that X is not a function of the variable Y means that X is not a cause of Y. So being a cause means that you have a direct relationship in the function of the variable, okay? So in this case, if we compute directly from the set of equations, we can compute this and see automatically that if I change the X, the equation for Y is going to be exactly the same, so I definitely have no difference. So the expectation of Y given do X is exactly the same as the expectation of Y. I have X is not part of the equation. So changing the number of firefighters does not change the initial severity of the fire. Okay, that's all. And that's now it comes to the randomized experiments that we are used to know, that we are used to believe that causal effects coming from randomized experiments are the biased causal effect. And how does this work, right? So basically, we leverage randomization of the assignment of the variable. So imagine that now I'm introducing here a new object for you. So this is the graphical representation of the set of equations. I will introduce later a little bit more about this. But here is just saying that Y can be affected by X, not the other way around. So I'm imposing here a structural assumption for the model. But there is this bidirected edge. That means that I can have several other variables affecting both X and Y. Those are called confounders. And it's in bidirected edge because I don't really know what are those variables that are not necessarily observed in my data set, but they are there. They are really important. So the variable X is affected. So if you get, for example, if you get data from a hospital about a drug and you see the output for example, a disease, the assignment of the drug for each patient depends on the history of this, the family history of this person, if the person has means to buy the drug, the age, the sex, and so on. So there are other variables that are affecting the assignment of the X. However, in a randomized experiment, I can randomize this assignment. And when I randomize this assignment, I'm removing or at least minimizing the influence of all these confounders. So when I separate this in a group where it's receiving for example, a placebo, or like one of the levels of the treatment variable here, that's the X, and another group that's now receiving randomly. So these two groups are separated in a way that they are randomly, we randomly assign who is receiving a drug 0 or who is receiving the drug 1. And because this is randomized, I minimize the effect of this by these confounders, which is represented by the bidirected edge. And then I can directly compute from the distribution that I observed, I can compute this quantity. And this quantity is exactly the one after doing this intervention on X. Right, so this the fact that I'm randomizing is mimicking this is basically removing the influences of the confounders, and the expected value of Y is going to be only affected by directed causes, right? So things that are directly connected to Y. So when I just get the sample from this experiment and compute the average in the group 0 and the average in the group 1, I get exactly the causal effect. Okay, I can compute the difference as well and see if this is better than, for example, the drug 1 is better than a placebo. And if it is a negative effect in this case, it would be something positive, right? So if I compute the same, if I randomized if I perform a randomized experiment with the number of firefighters, I would definitely see that the fire there is not changing. So if I have a way to do the experiment, I can basically use randomization to get the causal effect that I want. But the question that we really want here is like, can we identify causal effects without conducting a randomized experiment? There are many situations that is unethical, is not, many times it's not even, it's very expensive, so you cannot afford this, so it takes a long time to really observe the causal effect. So the question is, can I do this, right? And just to motivate you a little bit more, I want to show you these comics here. So it's from XKCD. So just let me read for you. So the guy here is observing, right? So there is a study here, another huge study, found no evidence that cell phones cause cancer. And then he asks, what was the WHO thinking? And then the other guy says, oh, I think they just got it backward. Huh? Well, take a look. So you are kind of observing a very large amount of data, and this is even over maybe 20 years here. So you started here in 1970s, and you are collecting the number of the total cancer incidence in each of these years. You also observe the number of cell phone users, and you see that they are very correlated, and even like there is a gap of around 20 or 10 years, I don't know, here 15 years, that you can clearly see that the cancer is first increasing, and then after a few years you see the same increase or similar increase in the number of cell phone users. So then the guy says, you're not, there are so many problems with that. And then the guy answers, just to be safe, until I see more data, I'm going to assume cancer causes cell phone. So he's here saying that just collecting more data is going to give you a more precise estimate about what would be the causal effect. What do you think? Do you think that he will be able to decide the true relationship just by seeing more data or not? He's not trying to perform any experiment, conduct any randomized experiment here, but he believes that over more years, just collecting more data, this is going to actually converge to the causal effect. Who here believes that this is true? Yeah. So data here can be very broad, right? The sense of data. So if this data is confounded data, no. Even in the infinite limit, you can get infinite data. You never get if this is the causal effect or not. Of course, you can have randomized data, data coming from randomized experiments. Then we are talking about something else, right? But observational data, no.
Yeah, sure. But in a sense, the data from experiments is also data. We observed a lot. We could condition on those kind of condition that we would have in the experiments without conducting experiments.
Yeah, I agree. So adding a lot of interventional data would probably refine your models up to a point that maybe you would get a causal effect. But my interpretation of this graph is that he's not even considering doing randomized control trials, because how you would randomize in this case, you have cancer incidence and cell phone users. You would have to randomize people with cancer and people without cancer, and then you kind of, okay, you have cancer now, you won't have cancer. So this is a problem that you can even have this interventional data, right? So, and unfortunately, why this is kind of an explanation that if you have two variables and you try to just get the association between them, there is an impossibility here to compute the causal effect. And why is that? So here I'm representing the functions as graphs again. So I'm saying to you that the model where the number of cell phone users, if you have a model where cell phone users causes cancer, I can play with the parameters and have exactly the same correlation that you're observing the data as if I had the other direction. I can play with the parameters and get exactly the same data that we're observing. So that's why these two models are statistically indistinguishable. Also, if there's no causal relationship between them, but there's like a third variable, for example, technology, that in my opinion, that's what's happening here. Maybe technology is improving, that's why cancer incidence is also improving. It's just you're detecting better cancer at the same time that this is making cell phones more accessible to the population, so that's why it's also increasing the number of users. So this could easily be explained by maybe technology. Could have both, yes, but the point is like all these methods, all these models behind this, you could be able to change the parameters of these models and get exactly the same observed data that you have. There is a problem of equivalence, and we will discuss a lot about equivalence here. Okay, so let's try to formalize a little bit more about what's happening and why causal data science has been very popular nowadays. So the theory was formalized a long time ago for several researchers. However, it became very, very popular because of Yuda Pro. Yuda Pro, he has this book, for example. He is a director of the Cognitive Systems Laboratory at the University of California, UCLA. And in 2011, he won the Turing Award. This is the most prestigious award you can get in the computer science. And it was exactly because of his contributions to artificial intelligence through the development of a calculus for probabilistic and causal reasoning. So it was his work on graphical causal models that actually gave him this prize. And he has a very interesting, I'm quoting here, this is a sentence from the Book of Why. So if you don't know this book, this is just it's like a book intended for people that are just starting or want to know a little bit more about why causal effects is different, what are the approach that exists behind in causal inference. But this quote is really interesting because it's connected to deep learning. And he says, deep learning has instead given machines with truly impressive abilities. So impressive abilities in the sense of prediction, right? However, it has no intelligence behind it. The difference is profound and lies in the absence of a model of reality. So it's connecting a model here. So it doesn't matter if you have just data. You need some constraints related to the model to kind of also constrain the space of models and see what would be the true causal model that generated your data. Oops, I'm sorry, there's some bugs here with my animation, but I cannot say that I cannot explain causality without citing also Guido Imbens, Joshua Engrist, and Donald Rubin. They are very important researchers in the field of economics and econometrics, and they developed, I would say, the first framework for causality was developed by all of them, with like instrumental variables, the potential outcome framework. Maybe you have heard all these frameworks out there. There is this book, for example, from Yosha Engrist that is about path analysis and using instrumental variables. The Causal Inference for Statistics, Social and Biomedical Sciences is a book from Imbens and also Rubin, where they show a lot of this, they explain the framework using potential outcomes. And some people believe that this is like completely different frameworks, but they are really not. Basically, they have just a different way of expressing the assumptions behind the techniques we have for causal inference. And Pro got very his theory got very popular because he explained these assumptions, and he even showed that the frameworks are all equivalent, so there is always a way to explain a method through graphical models, and this is more transparent, so you can always know what are the assumptions behind when you are applying some technique. So of course, if you want to assume more about the model, you have more power or more conditions for identifiability of the parameters. But at least he's showing this flexibility in the frameworks. And Engrist and Imbens, they won also the Nobel Prize in economics because of their contributions to causal inference, to the analysis of causal relationships. So you see, some people, this is really recent, right? The 2021. Moving a little bit more to deep learning, Yosha Benju is also working a lot on causality. He has this book, probably you all know about this. He's a professor in the University of Montreal, and he's also the director of Mila, and he has he also won the Turing Award for his work on deep learning. And he's working also on causality recently, and this is even a quote from an interview that he gave, saying that causality is very important for the next steps of progress of machine learning. So many important people are recognizing causality as the missing link, and I mean, there are several limitations still. We have a lot of open questions, but I would say that is exactly what would bring explainability, trustworthy, generalizability, and everything that fairness, everything that we are listening right now about what are the major challenges in AI. This could be addressed through causality, but we are still like, we need some developments to address all of this. So just to summarize here, why causality is very important. So the first thing that I mentioned is about the distinguish. It can distinguish between associations and causations, right? So it can determine the effect of unrealized interventions. And this is a topic that you can find in the literature through the name of effect identification or effect estimation. So it's very connected to the topic is explainability, and one of the particular case of explainability is fairness. So once you understand the relationships behind, there are some methods that allow you to actually learn from data what are the potential relations that you have between the variables. This is something that I'm going to also cover here in this lecture. That's called causal discovery. And once you can understand about what are the underlying mechanisms, we can also you can also design systems that are fair, or for example, infer effects that we call path-specific effects. So you can see if the mechanism that's or even for a prediction, if this is through some sensitive variables and that you want to avoid, so you can actually force that this is you can have like a zero path specific effect and so on. And the last one, no, I think that's the second to the last. So generalizability is also very important, because although even if suppose that you have the effect in one particular domain, suppose that I conduct some experiment in one population, you have the causal effect for that population. However, transferring this to another population or even to another domain, for example, you do some experiments in rats and you want to extrapolate this to humans. There is a huge gap there. Even transporting this, you have assumptions behind this. And if you put this in the language of causality, you can understand the assumptions behind this and do the transport using the correct formula, if it is actually possible. So the techniques are going to tell you if it's possible or not. And in the end, we also can combine all the knowledge and data that you have available. So if you have experimental data, observational data, expert knowledge, everything together, also you understand the difference between domains and so on, the language of causality can kind of encode everything in the graphical model, and then you can use tools to leverage these assumptions and then get your correct estimator in the end. So that's why causality, I would say, is important. It's basically formalizing the underlying assumptions. That's all. Okay? So questions up to this point? So how is this fair? Like, how is this connected to fair? So you have a break and a disruption, and then you want to know if this is affecting the cell?
It's a view running experiment. If something randomly happens in the world, it could be used to identify causal structure.
I mean, you have to model that event as something that happened in your when you're modeling your model, and then you can see what's the effect of this disruption in any other variable, maybe cells, I don't know. But yeah, you could model this, definitely. I'm not saying that you will get the answer. So the framework here allows you to model all your knowledge. So this is something that you can put as knowledge. I knew that this happened, so you can put there. And if everything else, data combined with this knowledge and maybe something else, allows you to infer what's the effect, you have it. So the framework is going to give you the estimate. So you can use this to see what's the causal effect. You can also say, no, this is not enough, because it could have a lot of confounders there that I cannot rule out the possibility of this not being causal, so I won't have the effect in the end. So that's okay. All right. So to basically also summing up a little bit more, there is this new field that we call as causal data science, where I would say the goal is not only do data fusion, so we combine these different knowledges or data sets we have available, but also allows you to do causal inference and decision making, is focused on decision making. So there is a difference between prediction and decision making. And that is this paper. It's already a little bit old, I would say, 2016. A lot of the methods that were here has a lot of advancements, but I would say that has many of the tasks that we have been working on causality. So if you want to at least know the keywords, I recommend this paper. It's by Elias Barenboim and Adele Pro. And around the same year, they developed this tool. So I really recommend you, if you want to play with causal inference, to sign up here. Please use your academia email, because Elias is the guy that's actually authorizing everyone, and it's being manually right now. And he will tell basically by your email if you are doing research or not. So if you sign up with your academic email, you probably get your registration very fast. But if it's not, you have to know that you are doing research, so you have to send an email and so on. But it's a really nice app. I will show some screenshots from this. And basically, you can draw your causal diagram, you can import data, and you can do causal discovery, causal identification. Yeah, not all the tasks are there, but to learn, I would say, is the best tool out there. I've been using for years, so I'm still learning a lot, so I still play with this to every time that I want to model some of the applications that I've been working on. All right, and if you want to also read books, I would recommend the Causal Inference Statistics as the first reading. It's a very, very short. I think you can read in like a few weeks. I don't know, a month maybe. It's really short. Like you can even skip the first chapter, but the others. But it's focused on causal identification, and there's nothing about causal discovery. And if you want causal discovery, you would have to get some other books. I can tell you later. But this book also has some, this is completely open, so you don't even need to sign up. So if you're reading this book, you can use this Causality 101.net app. It's also part of the other web app that I told you, the Causal Fusion, but this is open. So it's just showing the examples from the book, so you can play at the same time that you are reading. All right, and as I told you, the Book of Why is also a not good reading, and the Causal Inference Statistics is just this one that I told you. And if you really want like a very big reference for the field, that is the Bible of Causality by Udea Pro. It's not the most intuitive book, I tell you. I don't read it. I use it like, okay, this exists, it's perfect. What's the paper that this was explained? Then I usually go to the papers, but it's condensed. Like everything that I need is kind of there. And so I would just have as a reference book. I confess that most of the materials that I use to learn are the papers. So if you really want to know about the theory, you have to go to the papers. Okay, so let's formalize, going a little bit deeper to the math. It's not a lot, it's just very, I just need to define now what is the structural causal model, because the theory assumes that this model is the base of, or is the data generating model. And if you had it, that would be the full explainability. We are not trying to use the structural causal model in our analysis, but we need to know that it exists because it's the base of everything. It's the base of the framework. So the structural causal model is a tuple where we have 4 elements here. The first one is the set of variables you actually observed. We call it endogenous variables, right? So if you have a data set, it's the columns of your data set. You also have a lot of other variables that affect the relationship that you are interested in, those are variables that are not observed, so they are called exogenous variables, and they have this U notation, right? So the set U is always going to be variables that are not being observed. We have the set of functions that determine the so every variable in the set V is going to be a function of variables that are observed. These variables are usually denoted as parents in the graph, and everything else that's part of the function and it's observed is going to be called exogenous causes. So you have the endogenous causes or parents and the exogenous causes. And in the end, you also need a probability distribution over U. So if you have all of this, we also assume that the model is recursive. This has been relaxed for so a few years already. 2021 was the paper that it started to relax to have cyclic mechanisms now. I will tell you the paper later. But most of the tools that are available are still under the assumption that your model is recursive or there's no cycles or feedback loops. Okay, so this is the model. Let's just assume that it exists. Okay. You can tell me, oh, I've been working already on kind of something very similar. I've been using structural equation modeling. I basically write my set of equations. I estimate my parameters. Am I doing causality or not? If this is your true a structural causal model. So structural causal model is one of the examples is the structural equation model. The difference here is that you have to parameterize, right? So you have to tell how are the functions. So here, for example, I have 3 variables. Z is a linear function. Could be something different, right? So, but you need to write. You need to show me where are the parameters. You need also to specify if it is like are all linear functions, Gaussian variables. You need to specify what's the covariance matrix, the structure of it. And all of this exists is because you need identifiability of the parameters. It's like just to make the problem tractable. But these assumptions, if they are true, you have causal effect here. All these parameters that if you have, for example, this beta x0, no, this is the intercept, but if you have beta z xz as significant or different than 0, this means that z is a cause of x. So, but the question is, do I have the knowledge to ensure that this is actually the true causal model? Are my functions really linear? My distribution is really normal. When I say that these arrow terms are all independent of each other, this is equivalent to what we read in the field as Markovianity or causal sufficiency. So this is another assumption. This is equivalent to say that I have no confounder in my system that has not been observed. So if you've seen, like if you have this model and you assume here that the error terms are all independent of each other, you are under this assumption that you observed all the confounders. This is something strong. But if you are under the scenario, that's easy, right? So you have basically the full specification of the structural causal model. It's requiring some assumptions, and if they are all correct, you have the causal effect. But most of the times we don't have the knowledge for this. And okay, let's see what would happen if I don't have the model then. So, okay, this model exists, and I'm putting here in red just to call your attention here that the variable x and y are being correlated, not only because x is a cause of y, but also because there is this variable that's in the U set, so it's unobserved, that's affecting both x and y, so it's a confounder, okay, and it's unobserved. If you just collect data from the system, you don't know the system, and not even writing the functions here, you just collect data. You have the observational data, you can estimate the observational distribution. This distribution tells you if for example, x is correlated to y, and then you can use this to do prediction, to make guesses, like the firefighter example, okay? However, this is completely different if you want to have the causal effect, because now the causal effect, when you have the model, the effect of changing the variable x to a constant is represented here by replacing the function of x to a constant, right? So this was before a function that was being influenced by some other variables, some of them even confounders, but now it was replaced as a constant. When you have the model, you can basically do this manipulation, get the induced distribution from this, and then you see this distribution is the interventional distribution. So if the probability that you have from induced by this model is the same as the one, so now you see that there is this mx is because it's this model, but if you have any difference between the probability, for example, y, I get the probability of y coming from this model where I intervene on x. If the probability of y in this model is different for any x, is different from what I had before, is because x is changing something in my variable y. So x is a cause. But if it's not, then x is not a cause. So if you have a model, it's pretty simple. You just replace the function, get the induced probability from this, and that's it. But usually you don't have it. So you have these laws of information. You have from the model either observational data. In some scenarios, you can estimate the observational distribution, and you can also impose some structural assumptions, for example, represented in a causal diagram. When I move to the side of where I have an intervention on x, Then I have interventional data, I have the interventional distribution, and the model is the one where I have no adds into X. So this is called the manipulated graph. And because of these laws of information, we usually work with these objects, not with the model, right? So what happened then? So suppose that I have this true model, okay? And I don't know, it's in red here because I don't know anything about it. The problem is that this same model can induce a causal diagram where it's actually following the orientations that I explained. So X is an argument of the function of Y and has some confounder here. However, okay, and this induces some data, okay? However, there are a different model under the different parameterizations, but it's still preserving the same structure in the sense that X is an argument of the function of the Y, so I'm just changing the functions or the distributions. And so this is still inducing the same diagram, and worse, I can play with the parameters and get exactly the same data. And there are many models that do this. I can also change the models in the sense that it's changing the structure, so flipping now Y as an argument of X. And again, playing with the parameters, I can create some models that's going to create exactly the same observational data. And that is this equivalence that I told you. You can have all these different models under all these different graphical representations, and they all can generate the same data. So what I'm telling you here is that if you want to describe the functions and be in this side of the of my panel, here in the right panel, you are picking a model. And if you pick a model, you need to be very certain about the assumptions that you are adding here, because if you're just learning, for example, I have here, so here I'm just putting in gray that those are the cases where I have no unobserved confounder. So even in the case where you observed all the confounders, there is still equivalence between the models. And you see that I'm adding assumptions as I'm going to the right here. And if I just fit a model, for example, let's train a neural network on my data. And what will happen there is that I'm going to get one of the models in the right side, and just it's fitting. My goal here is to fit my observational distribution. So any of these models here is going to have like very good accuracy in predicting the probability of Y given my set of predictors. However, getting explanations about this model that you fit to the data doesn't tell me much about the true data generating model. You can get full explainability about this model that was fit to the data, but this can be like explaining this model here, not the true one. You don't have the guarantee that you pick the right one. To get the right one, you have to induce, for example, structural assumptions, and then you kind of refine the set of equations that you can fit on, right?
Is there a one-to-one within the causal diagram and the SCM up to a parameterization? So if I still use the same functional dependencies, they all correspond to a single causal diagram?
Yes, it's only one. Because I didn't put here the slides because I thought it would be too much, but basically you get an edge every time that one variable is an argument of the other, right? So here, if X is an argument of Y, then you put the edge, the directed edge. If that exists any other variable that's an argument of both, you put the bidirected edge. So there's only one. If you have a set of equations, you just follow this procedure and that's it. Okay, so in the first lecture, we talked about Bayesian networks, and many of you kind of asked if this has a causal meaning. And Bayesian networks is not trying to capture, so by causal diagram, I want to here explain the difference between Bayesian networks and causal Bayesian networks. So that is a difference. Causal diagrams following the structure of the causal model, the structural causal model, is different than just a Bayesian network. A Bayesian network can even have latent confounders. So most of the definitions of Bayesian networks is under the assumption where you don't have the bidirected edge, but here I'm going to show you a definition that extends or generalizes to the case where we have latent confounders. And the goal of Bayesian networks is to represent conditional independencies. That's the only goal of a Bayesian network. Okay, and we saw in the first lecture of the summer school what is this separation. I'm just going to review just a little bit because maybe you forgot. So we have in Bayesian networks, we have these triplets. Here I'm not showing bidirected edge, but it would work in the same way. And these triplets are important. So usually look at triplets and you try to figure out what would be the conditional or the marginal dependencies and independencies between the variables. So here we have a fork. A fork is because z is like a fork into x and y. And you see, I have an example where x is obesity, z is age, and y is baldness. And this is an example where x and y, you have a flow of information. This path is open, right? And if I have this is encoding that x and y are marginally dependent, while if you condition on z, since z here is a non-collider, if I condition on z, then I have x independent of y given z, right? So this triplet is representing these two constraints, x marginally dependent of y and x independent of y given z. So if you think in the example, it's like you can see people that are obese and bald, and they are going to be probably, if you just measure the number of people that are obese and the number of people that are bald, you see that there is probably both, like as if you it increases, right? It's like positively correlated. But if you condition on age, then you don't see this anymore. It's because like people that are older tend to be more obese and tend to be, in the case of men, maybe bald, right? I don't know. This may not be a very good example, but you see that there is like a way to block the correlation between the variables, and this is like conditioning. Once you observe that the age is what's the age of the person, you don't see this correlation anymore. You have this other one that's called chain, because you have like now a chain of information. And I got here this example where family history of diabetes affects the propensity of having diabetes, the person himself has diabetes or not, and also diabetes affects the propensity of having a stroke. And if you don't know, for example, if the person has diabetes or not, so it's just looking at the family history of this person, you can guess what's the probability of having a stroke, because if your father had or your mother have like diabetes, maybe you have or not diabetes, and this affects the chance of getting a stroke. So there is a flow of information. But if you observe, no, I don't have diabetes, so now this correlation is now blocked, right? So you break this correlation, because once you know that the person has no diabetes, then the decreases a lot the probability of having a stroke. So it's again a non-collider, and this represents again the same set of conditional dependencies and independencies. So you see here, both of them are representing cases where x is dependent of y and x is independent of y given z. And you see, the edges are different, but they're encoding the same information. If the information that you can get from the data are dependencies and independencies, statistical associations, both of them are perfectly representing your data. And having the meaning of causal is something more. That's not in the causal, in the conditional dependencies and independence. You have other structures, however, that are more special, I would say. And this is the case of the collider. Why? Because if you see this example here, is an example where you also saw in the first lecture that the collider blocks the information. So if you see diet and physical activity, they are kind of uncorrelated, right? They are independent of each other. If you see that the person is like, this is a simplification, so it is not really that if you probably exercise a lot, you have a better diet, I don't know. But here's a simplification where they are independent. However, imagine the case where a person is obese, and also, now it's conditional on the fact that the person is obese. And the fact that you know that this person exercises a lot, what can you tell me about his diet? So now you see, I just have physical activity. The person exercises a lot. What can you tell me about the diet? Nothing. But once I tell you, this person is very obese, very, very obese, what can you tell me about his diet? It's very, very poor, right? Very poor quality, very poor diet. He's eating a lot of sugar, fat, I don't know, a very simplistic model. But you know that now Y is correlated to X. Once you observe that the person is obese, or once you condition on obesity, X and Y are correlated. So it's the opposite of the other examples. So now X and Y are independent marginally, but once you condition on Z, you have dependence. And you can also condition on descendants of colliders, and this has the same effect. So if you have, for example, now the information that the person has a heart disease, you don't know about the obesity or not, but you know that it has a heart disease. So kind of it's a proxy for obesity. So it's the same reasoning. So you see that this is the only structure. So these are the three most important triplets in causal discovery that if you have like this set of this list of conditional dependencies and independencies, you can kind of figure out what are the possible orientations. Because if you are in these two scenarios, you don't really know what's going on with this, with the Z, but in this scenario, you have the case where this is a collider. Okay, and so Bayesian networks are encoder of causal independencies. So the goal here, the only goal, is that every time that I have a disseparation in the graph, I have the correspondence independence in the probability distribution. That's all. There's nothing more than that. And it's expected to be minimal, right? Because I could have a full graph here and this would be satisfied trivially, so I don't want this. I want also that no edge can be removed without seizing this property. So it's a minimal independence map. And if I have that, then I can kind of factorize my distribution in a really nice way, because I can factorize in terms of the, so each variable condition on the parents that are observed and also in the causes that are unobserved. So you have this factorization. So it's just the goal of Bayesian networks is representing the observational distribution in the most simplified way through this factorization. That's all. Okay? So there's no causal semantics. So this is just an example. You can play later with this, but you see here through this separation that some variables are independent of each other. So you start with the joint distribution. This is just the chain rule. So you apply this to any topological order. And once you start applying the independencies, you can simplify the terms, right? So you have, for example, several terms where you can correspondingly simplify, and you see later that this is respecting the fact that each variable is conditional on the parents. So we started with the graph, and then you factorize, not the other way around. The other factorizations corresponding to other graphs would also work. And this is what we are going to see in the Markov equivalence class. So if you have data, right, so many models imply the same data. It's in red because you don't know what's the model that generates the data. You just get conditional dependencies and independencies from the data. Suppose that I just have the fact that X is correlated to Y. I can play with this factorization of the joint distribution, and you see that I cannot simplify anything, but it is still respecting the fact that variables are conditional on their parents, and this is going to correspond to like multiple graphs. And then this list of graphs that explain the conditional dependencies and independencies in your data are forming a class that we call it Markov equivalence class. And this is the proof, the kind of illustration, I would say, that the association doesn't imply causation, right? Because they are all here representing the same information. When you change a little bit, suppose now that from my observational data, I have now the information that the only independent, so everything else is dependent, that X is independent of Y given Z. So you start again playing with the factorization. So I can start with the chain rule, then I start simplifying using the only independence that I have. And you can see that this is forming, for example, Z here is a parent of Y, X is a parent of Z, and X is alone. If I play it with I use another topological order, and then I use again the condition dependencies. I have a reverse chain. I can do again and then have a fork. And this is like using, without using an observed confounding. I could also add an observed confounding. This would be now the example. So you see I can play, and you can show now you would have to marginalize the variables u, but you see that in the end you would have exactly the same factorization, and then you would get a larger class of models, all representing the fact that x is independent of y. So from this list of models here, I don't have many invariances, except by the fact that you don't have an edge between x and y. So you can see that all of them don't have an edge between x and y, but that's all you can say about what's common among all of them. And so you can say here that there is an invariance, that z is never a collider. This is something for sure. You never saw a collider here. So you can play now with these invariances of the class. If you change now to the case of the collider, so let's suppose that x is independent of y. I can do the same reasoning. I start here with the joint distribution factorized using the chain rule. Then I use the fact that x is independent of y, so I simplify this factor. And now I have, for example, this case where x and y are parents of z. Okay, and x and y are alone. And you can now add the an observed confounding. If you do at home, you see that you can marginalize the variables u, and then you see that all of them are representing the fact that x is independent of y, right? So you can play again with the separation. You also see here that x is independent of y. But now it's more interesting, because you can see here that if we look at all of them, you see that z is a collider in all of these models, right? So that is an invariance. Z is always a collider, means that z is never a cause we will call ancestors, because it doesn't matter if it's directed edge or like a true path, entire path, but this means that z is not a cause of x and y. And this sometimes is a good information, right? You know for sure that you cannot intervene on z and expect a change on x and y. Okay, so now moving to causal Bayesian networks. Why is different when we assume that you have a causal diagram? A causal diagram is not only encoding condition dependencies, but it's also encoding causal and confounding relationships. So the structure causal model, suppose that that's my causal model here. And now I said that I don't have the slides. I have it. Basically, that's the definition of causal diagram. So how can I construct the causal diagram? I just look at the variables in the set V, okay? And for every pair of my set Z, I will add an edge if Vi appears as an argument of the function that defines Vj. That's the Fj here. So in my example, you see here, I don't know if you can follow, but I can explain to you. So C here is a function that depends on B. So B is here. So see, I'm just looking for variables in the set V. I'm not considering the variables U. So B is here pointing to C. Who is argument of my variable B is like A and D. A and D are arguments of the function for B, so they are also have edges there. And you would have, if I had all the U's observed, I would just follow and have all these other nodes pointing to my variables. However, the way that you represent the unobserved variables in my graph is the following. I will only represent variables, and it's going to be through this bidirected edges, if let's skip this because this is, I will explain later, but if first they share the same argument. So for example, UCD is both as in the function of D and also in the function of C. So that's creating a confounding between them. All the others are just pointing to one variable, so it's not shared. They are there, so when you have a causal diagram, you see that there are other variables pointing, but they're they are not showing. But the confounders, they are going to be represented as bidirected edges. Okay, because those are the only important for analysis, but the others are there. And just to not have a lot of nodes pending there, I just hide them, but they are there. Okay, and I said that let's skip this because you could also have the case that the U's are correlated, and this is like when you project it, you also have a confounder. So let's go back here. Suppose that the U's are correlated due to some other variables, then if you project in the end, it's kind of the same as having one confounder. So this is just redundant. So every time that you have like one ancestor of both, you can add the bidirected edge, right? So causal diagrams created through this process, so it's induced by structural causal model, it's called causal Bayesian network. And it's not only encoding the condition dependencies as a Bayesian network, but it's following the causal relationships. It's also encoding the confounders. So that's the difference between them. And because of this, you have something that's more powerful. This graph, we call it a cyclic directed mixed graph instead of DAGs. Many times you learn that Bayesian networks are DAGs because you don't have this bidirected edge. But if you have the bidirected edge, we call it ADMGs. But ADMG, if it follows the structural causal model, then you not only can factorize the joint observational distribution, but you also factorize the interventional distribution. So here, the interventional distribution can be factorized. So now it's the do X here is factorized by the variables given the parents, and this is conditional on the fact that X is equals to X, so you don't have here the factor for the X, because the probability for X is 1. But so the parents here are not just variables on the Bayesian network pointing in the direction of the variable, but also they are actually causes. Okay, so that's the difference. And we call it this truncated factorization. Okay, now that you know there are differences between Bayesian networks and causal Bayesian networks, it's now time to know that we also have different layers of inferences. And this was explained in the book of UI. We will have a picture of the prose causal hierarchy in the next slide, explaining that there are actually 3 different layers of inference. So this is the picture. And the first layer, it's called scene, because that's where we do prediction. So we only need here observational distribution. That's all you need. So we find associations, and the language that you need is just what, for example, Bayesian networks, and actually any machine learning method, because your goal here is to get a good model to represent the observational distribution. That's all. And with this model, you can answer questions. For example, how would seeing X change my belief in Y? Like it's a guessing problem. What does a symptom tell me about the disease? So I'm just observing, I'm not changing anything, I'm just observing and make predictions. This is different than interventional queries. So this is the second layer of the ladder of causation, and this is dealing now with the interventional distribution, and now we need causal Bayesian networks. We need something more. Reinforcement learning is also something that gives you the causal effect because you play with experimentation there. But then if you have a model that came from this knowledge that's interventional, you have now the possibility of answering questions like, what would Y be if I intervene on X? There is a decision-making now process. Will my headache be cured if I take an aspirin, right? And this is still different. There is a third layer of inference that's called counterfactual. That's even harder. You need more information. So as you're going up this ladder, you need more and more information. So we started with just data. Then we needed something more, for example, the causal diagram. Now we need something even stronger, which is the structural causal model, to answer questions that is now related to alternative realities, like is the imagination, retrospection, like what if I had acted differently? So I took an aspirin and my headache didn't stop. So what is the aspirin? Was it actually the aspirin that, in this case, it stopped my headache? Was it the aspirin that stopped my headache, or the other way around? If I hadn't take the aspirin, would actually my my headache would stop? And so this type of reflections, and is really, and we can see it as a more individual level of inference. So individual causal effects are usually in this counterfactual layer of inference. They require more information, more than usually the causal diagram to be able to answer. So there are actually cases we will see where you can infer causal effects only through data, but it's not the full interventional distribution. There's also a case where you can infer some counterfactual effects just through the causal diagram, but it's never the full counterfactual distribution. That's always here thinking about in generality, okay?
Explain what in the causal base net also has a diagram, is that right?
The causal Bayesian network is a causal diagram.
Is correct by a causal diagram. What additional information is in the structural causal model that can't be characterized by the diagram?
The diagram doesn't is not telling you anything about the type of the functions. Could be linear, could be non-linear, could be like have interaction effects, could be anything. Also doesn't tell you about the distribution of the variables, can be anything. So it's fully non-parametrical. So when you have, of course, we are talking here later about condition independencies, and you need then an oracle of condition independence. So here we are using this separation, and if you had data, this would be necessary to, like, if you are testing, we would need something like a test available to test this, but the graph is not telling anything about the type of variables, the type of functions. Okay? Any other questions? So that's the challenge here. How can you move across the layers of this ladder, right? So how can I use, for example, data? Given that I have data, how can I do causal inferences? And there is this causal hierarchy theorem that says that the ladder almost never collapses. That's what I tell you. So collapses mean that just having data would be sufficient to infer any causal effects that I want. So this would like being collapsing, and this is never going to happen. Like, there are cases where you can actually infer causal effects just from data. We will see this by the end of the lecture. However, learning the full causal, learning or inferring all the effects between every variable that you have available, you'll be almost impossible from only data. You need more. Okay. So that is a pipeline. That's what I'm going to try to cover. Just a little bit about any of these parts here. The next after the break. So we have here basically 3 inputs. Usually it's like a question that's in terms of interventional distribution. Could be a counterfactual distribution here. The number 2 are the assumptions that you are making. Could be learnable from data. Could be imposed by knowledge. Could be some more relaxed, some parametric constraints, could be anything, but these are constraints related to your model. And then the 3 is usually distributions that you could estimate from data that you have available. You could have a collection here. Doesn't need to be only observational distribution, could have more. And then you have like several tools. These tools are going to put together all this input. And it's going to usually, so the goal is like to check if the input that you have available that you did through causal modeling or causal discovery is going to see if this question that you are asking is possible to be answered. So you can have a yes or no solution. You can have like cases where this is not sufficient. But in the case where it is sufficient, this means that the data that you have available, the constraints that you have available, it's sufficient to transform or to have a mapping between the distribution that you want to infer, which is, in this case, is the interventional distribution, as a function that is only in terms of the distributions that you have available. In my case, it's just observational distribution. But you see here that all the terms in the right side are able to be inferred through this, the number 3, which will be data that you have available. And of course, you can, from the distribution, can get the expectation, you can do whatever. So that's the mapping. And then once you have this formula, you get the data again to get the effect estimation, because you have to play, now you have to use here you see that the input is the true observational distribution. But with data, you can infer the observational distribution to actually have estimates for each factor of this function. So that's finished my pipeline. That's all you need. So you need to do this in 3 different steps. Okay, I will move now to, it's a kind of flipped here, the reason, like I showed you the pipeline before the break, where we start doing causal modeling, then causal identification, and then causal estimation. I'm going to start with causal effect identification, assuming that you already have the causal diagram in hand, right? So you can construct this by knowledge. And I will go back later in the end of in the middle of the lecture to explain how can we use data to learn a class from data, a class of possible causal diagrams. But I will start with this because this is how the theory evolved. So basically, if you start reading the Book of Why or any of these Pearl's book, it's going to be always assuming that you have the causal diagram in hand. Of course, now the tools have been relaxed to accept the output of causal discovery models, but I will start with this just because most of the methods are still in this stage. So as I told you, causal effect is just a quantity that's going to be derived from the interventional distribution, right? And as an example, we have the average treatment effect. This is very common, and it's basically the difference between if you have a discrete treatment, so X here is a discrete variable, and you can have like different levels. You just pick 2, and then you get the difference between like the pairwise difference. You can see how much one level is different from the other level in the effect, in the expectation of Y. So this is a very common quantity that people are interested in. If you have, so this is just showing how you would derive from the interventional probability. So interventional distribution is just a probability distribution. So everything that you knew about how to operate with probability distribution, you can operate on top of this. It's exactly the same. If you have a continuous treatment, we have the average treatment effect as defined as the derivatives of the expectations. You can have like partial derivatives, but this is again just showing how Y changes with respect to interventions on different levels of X. This is just the usual way. Then, as I showed you before, we have this pipeline here, and the first tool that we have available that's like automatically identifying effects is started by assuming that these causal constraints are encoded as a causal diagram, right? So we have causal structural constraints. And given these structural constraints, plus in the case where you have the observational distribution available, or at least data where you can infer the interventional distribution, you would use you would use other tools as well. So we had a few graphical tools first developed. I will show one later, but I would say that in practice, you go directly to ID algorithm or identify algorithm. That's the reference here is an algorithm that's a complete algorithm developed by Jin Tian and Yuda Pro in 2002. And it's complete in the sense that if you have a no answer from this algorithm, so if it fails, it's because the input that you have available is not enough in the sense that in the class of modules described by this causal diagram, you would have the effect identifiable in one of the models and not in the other, or it would be identifiable through different estimates. So you don't have identifiability in the sense of getting just one equation to infer the effect regardless of the model that generated the data. So the algorithm sometimes gives you a positive answer, and if there is a positive answer, now it's a different formula from the other slide that I gave you. So this is sensitive to the graph. So depending on the graph, you have a different formula, but it's still, if you have identifiability, this means that the interventional distribution that you are requiring here, it's written in terms only of the observational distribution. So you have a way to use your data and then estimate each of these factors and then get the distribution as if you had this performed this intervention. Right, so you have this mapping here. Note here that this is knowledge, that is, you need to use knowledge to construct this causal diagram. The effect identification problem, you just skip what's written here. I'm going to give you the intuition. Basically, is like you have a true model, but you don't know. Like this red block here is just showing, I don't know what is this. But it actually induces a causal diagram. I'm assuming here you have knowledge to construct it. And you have, for example, data where you can estimate your observational distribution. Not all models are compatible with both, right? So we saw from the list there that just a few are compatible with the diagram. And there's now just a few that are compatible also with the distribution, because changing the parameters, you also restrict the set of models that are compatible with this information. Identifiability here means that doesn't matter. So doesn't matter as long as you are compatible with these two information. You have an interventional distribution that you work for all classes of models, for this entire class of model that's compatible with both. Maybe a different picture here that's going to help you is like this diagram. So in yellow, we have all the models that are inducing your observational distribution. And we have in blue all the models that are compatible with the structure, the causal diagram G. There is just a few that are compatible with both. If for all of them, we have only one, the same interventional distribution, then you have identifiability. If for some of those models, we have a different interventional distribution, then you have no identifiability. So every time that the algorithm, so as I said, the algorithm is complete. If it gives you the answer, it's because doesn't matter which model you have, since it's compatible with this distribution that you have available in the causal diagram that you gave to the algorithm, all the models in the intersection here are going to be identifiable through the same equation. So you can just infer this, estimate this estimate, and then you have the interventional distribution. Okay? So I told you that there are easiest ways of, when you learn about causality, usually you learn like 2 by 2, and then we have a calculus, and then you understand how the calculus is connected to the algorithm. So you learn a lot of tools and how they are actually developed internally. If you're just a practitioner, you don't really need. You basically just apply the ID algorithm blindly, and that's it. But here I'm going to try to provide you just a few of those tools just for you to have a feeling, right? So of course I won't be able to explain how the ID algorithm works. This is actually maybe a 2-lecture to actually explain, but here we have some very easy tools that I would say that are even the most useful ones. So the first is like adjustment over parents. So imagine that you have the situation where all the parents, or when I say parents, here I assume that you have the causal diagram. So you have actually all the direct causes for the variable x, that's the treatment variable. This is almost as if I'm requiring that I have all the confounders observed. In this scenario, basically, I have identifiability always. It's very easy. Like if I have all the parents, my distribution here, this is the interventional distribution for computing the effect of X on Y, right? So this probability, this conditional probability, is given by this summation here. This is called adjustment. So every time that I call adjustment, we are assuming that I'm going to control for these variables that are called parents. Let's see a graph here. So this is a graph that's not, I have some unobserved confounders, as you can see through this bidirected edges. However, both parents of X are observed. I don't have bidirected edges between Z2 and X and between Z1 and X. In this case, how does this work? Basically, by conditioning on the parents, I block every path that's creating a confounding between X and Y through this separation. So the only paths that are free to actually move, to flow information are the directed paths. So that's why this adjustment here, where I control for the parents, removes or eliminates the influence of the confounders, and then I have in the end just the effect through the causal paths. That's the idea. But if you are under this scenario where all the observed parents are given to you, you just apply this, and doesn't matter who is X, who is Y, as long as you have the parents of X, you just put this in the estimator. And why I'm telling you this is truly strong, right? However, that's kind of the scenario that if you are under the potential outcome framework, many people argue, oh, you can kind of justify you are under the unconfoundedness scenario. Sometimes you have this unconfoundedness assumption, and you can be in this scenario if you have all parents observed. So I have to bring here, because if you know a little bit about the potential outcome framework, this is one of the justifications that they have if you have the parents. But follows basically from the factorization under the Markovian scenario. So if you have no U variables, it's really easy to kind of prove that this works from the factorization of the truncated factorization, the factorization of the interventional distribution. You can try at home if you want, but it's not hard. But I just want to bring this because this also gives you motivation for the next two, which is the backdoor criterion. This is, I would believe that if you learn at least this two from today, you'll be like better than 80% of the practitioners of causal inference out there. It's like most of the times that I have to apply, I end up having to use this. Either the idea algorithm works for general graphs. This is the scenario where most of the cases are under with. And it's also the scenario where if you are using these out-of-box or out-of-shelf tools, they are assuming this scenario. Okay? So what does the scenario mean? It means that let's focus that you have a set of variables X. So not necessarily just one variable, can be a set of treatment variables and a set of outcome variables Y. And that's going to be your graph. It's very simple. Like X is affecting Y, and you have confounders. And this is just one case, but you need to look now for every path that's into X and also into Y. These paths are called confounding paths, or also backdoor paths. And through the separation, if you can block all these paths by conditioning on a set of variables Z, you are, sorry, there's one condition. Let's see the conditions here. So the first condition is that you separate. So it's the same as what I told you before, but it's first removing the directed paths, which means like you remove every edge that's out of X. So you are left only with the confounding paths. And if you have a set Z that separates X and Y, it's the same as blocking all these confounding paths, you satisfy condition 1. Okay? But you have a second condition. The second condition is that no node in Z can be a descendant of the variable X. So you see here that Z is pointing to X. So this is like an ancestor of X. We use like family relationship. Would be a descendant if X was pointing to Z, right, as a child or even more, but cannot be a descendant. So as long as your set of variables Z blocks or leave all confounding paths blocked, you have the set Z, and then you can basically compute the effect through the same formula we had before, which is called adjustment, but instead of having the parents, we have the set Z. It's very intuitive. Like I really would like you to leave here knowing at least these two. Like you just need that a set of variables Z blocks the paths that are both into Z, into X and into Y. Those are called confounding, okay? And you use this separation. Let's see some other example. Another example where I have like a set X, which is X1 plus X2, and just Y. I do the same procedure. So first I remove the edges out of X. So I'm going to remove X going out here to Z1, and this other one out of X2. What I need now is to find a set Z that blocks all the paths that are into one of the X's and Y. So into X1, there's no path. So I just ignore X1. Into X2, there is only one path. That's this one here. So if, for example, I block, how can I block this path? Like I have two non-colliders. I can block by just conditioning on Z1 or conditioning on Z2 or conditioning on both, right? So here, if Z is like Z2, then it works. Or Z equals to 1, but that's fine. Let's see more examples. Now I'm going to ask you, which set Z here would block the confounding path? So first of all, what's the confounding path here? It's a path that's that's both into X and into Y. Is this path? No, right? It's this path. So how can I block this path? Which variable?
Z2 or Z1, it doesn't matter.
Exactly, doesn't matter. And second question, is this including any descendant of X? No. So it's fine, right? So all those three sets are admissible for adjustment. I can condition on Z1 or Z2 or Z1 and Z2 at the same time and put in that formula, and this is going to be my interventional distribution. Now, that's, for example, the example with Z1. Now, yeah, we have the minimal, which is like just the ones that have the fewer variables. Now, the second example here. So I have to block the confounding path. The confounding path is the same one, basically. But first question is it blocked already? It is, because it's into X as it's into Y. Right? So any path that's kind of starting on X, a path is just a sequence of edges, doesn't matter the direction. Okay? So this is a path. And it's starting with an arrowhead into X and finishing with an arrowhead into Y. So that's a confounding path. Then I have to ask if through this separation, I mean, it's hard to call this separation here because this separation usually needs to block all the paths. So first we need to remove all the edges that are out of X. So we are going to be only this path. If you block this path, then you disseparate X and Y in the graph after removing the arrows out of X. We can also call block all the confounding paths. This is different than disseparation. But we use the disseparation rules to see if this path is blocked. So to be blocked, don't know if you remember, I need at least one of the colliders as not part of the conditioning set, right? So I have this collider here, Z1. So this path is already blocked. So this case, the empty set is admissible for adjustment, which means that I don't need to have the Z here. So if I don't have the Z, I don't have the sum. So which means that observational conditional distribution is the same as the interventional distribution. You don't need to condition on anything. You just get the probability of y given x, this is your interventional distribution. But you also can condition on other stuff and it still be fine. If you condition on Z2, you're not hurting, it's still blocking. If you condition only on Z1, it's bad. So if you end up having a data set where your variable is Z1 and you condition on Z1, you're just getting a biased effect. You are inducing more correlation to X and Y. But if you condition on both Z1 and Z2, then you are opening this collider, but you are blocking this non-collider, so you are still fine. So the selection of variables for this backdoor criteria is really important, right?
You mentioned that the empty set is also enough for having just the two operator for X. But there is this thing that Y is also taking Z2 as an input. I mean, Z2 is the parent of Y. So is it
Z is not parent.
Z2?
Z2, no. I need that the variables on Z are not descendants of X. So Z2 is not a descendant of X.
But like, if we, given a data set such that we are, or given this graph, we would be saying that if I set X to something this, and I'm trying to observe the probability of Y, but this probability of Y would, is also taking an input from the Z2. So is it that we are marginalizing out the Z2 or?
No, you have the marginal probability of Y, ignoring other two. You can compute the marginal probability of Y without, you know that Z influences the Y, which means that the probability of Y given Z2 is different than probability of Y, but you can compute probability of Y. It's just marginalizing the joint to just have the Y. You can compute this. I'm not asking you. So this is a different, maybe you're confused because when I ask you to give you the best prediction, you kind of tries to leverage every information that helps to predict Y. I'm not asking you to predict Y using the best information. This would be probability of Y given X and Z2 in this case. I'm asking you, that I'm telling you, to be honest, that the probability of Y given do X, which is the interventional distribution of Y after performing an intervention on X, you only need the probability, you only need to compute this conditional probability, the probability of Y given X. You don't need to use Z2. You can throw away your data. This is not necessary. Of course, you can use it because Z2 is not hurting. But this is going to be equivalent to, so this quantity by summing, because now you have to summing out Z2 here, this is going to be equivalent. You have the same expression in the end. And if I compute Z1 and Z2 is the same. And actually adding variables, you have a problem here to increase variability. So it's usually the best to use the minimal conditioning, the minimal adjustment set, right?
Basically, it can also act as a feature of descriptor reduction, like feature reduction or feature elimination.
Yeah, but the feature elimination has to be through this criterion. Yes, you cannot use others because Z2 helps to predict Y. So you use like feature selection for prediction, Z2 will be important. But I'm telling you, this is a different quantity. And one of the methods, which is this one, tells you that you don't really need the Z2. It's counterintuitive because you're thinking about prediction. And predicting Z2, in this case, it doesn't hurt because Z1 is blocking the information. But if you use Z1 and not Z2, you are kind of giving you a wrong quantity. So you are giving the information that predicts Y, that's not through the intervention on X, it's through this confounding path. So imagine that you have no edge between X and Y, and you try to, and then you get a new condition on Z2. You see it's possible to get, for example, a probability of Y given X0 that's lower than the probability of X equals to X1, and this X1 can be a drug. So you see a difference between two probabilities, and then you say, it's because of X. No, But I'm conditioning on Z1. I'm controlling for the confound. No, you are adding more confounding by conditioning on Z1. So the quantity that you want is the one that's free of the influence of the confounding. Okay? More questions? All right. So what about this? The empty set. Very good. Why? It's just the empty set or no? Yes, so no. Why not others? Just the empty set, because Z2 is a descendant of X. Sorry, well, X is a descendant of X. Z2 and Z1 are both descendants of X. So you violate the second condition. What about the last one? I have two confounding paths now. Let's try to fix the first. Let's pick this one here, the larger one, the longer one, through Z1 and Z2, because it's similar to the others. So we saw here is similar to the first, right? So we saw that we could condition on Z1 or Z2 and would be all fine, right? But I also want to block the second. The second is already blocked. But I need to condition at least one of them to block the first. Who would I pick, Z1 or Z2?
Z1, because Z1 has a confounding variable.
You would like to have what?
Z1.
Z1? Okay. If I get Z1 now, I'm conditioning on this collider, and this path is open. So I block the first, but I open the second. You want to try the Z2? Z2 is a descendant of the collider. Also blocks the collider. So there's no way to use backdoor adjustment in this problem. This problem actually ends up to be not identifiable, but there are cases where you would be able to identify the effect through ID algorithm, but not through backdoor adjustment. So that's why the backdoor adjustment is just one of the tools, and it's not complete, but it's easy. Like every time that you get a problem in your hand, let's try the backdoor adjustment, because if you get the problem solved by this, it's really easy to solve. But there are cases where you end up with this graph, you try backdoor adjustment, the algorithm is going to say there's no adjustment set for you. If you condition on Z1, you won't get your causal effect. If you condition on Z2, you won't get your causal effect. If you condition both, you won't get your causal effect. So it doesn't matter. I would have to try other tools or add more variables here to explain this confounding, to then be able to really block. So if, for example, I have an edge, a node between Z1 and Y, then it's okay, because I open this collider on Z1, but I condition on this other, and then I would be fine. So observing a variable between Z1 and Y would help me to solve this problem through adjustment. So you kind of can analyze your problem and see if you need to go back and collect more data and so on. Okay, through causal fusion, you can basically do this using the tool, so you don't need to apply the criterion by hand, like knowing the separation and all. So you can basically draw your causal diagram and ask here what's the effect of X on Y, and it's going to give you the formula for you. So you can draw different causal diagrams and see if your effect is identifiable. These three, you have Z as the adjustment set. You have this other one. This is a case where, again, you don't have identifiability, because if you condition on Z, you open the collider. If you don't condition on Z, you leave the open path through this directed edge. So it's, again, a non-identifiable case. So if you condition on Z, you are getting some correlation between X and Y, but this is not the causal effect. Okay? I also want to show you a counterfactual interpretation of the backdoor, because if you are, again, from the potential outcome framework, you are used to see this assumption here, which is really weird. There is this subscript X here, but it's the potential response of the variable Y under an intervention on X. So in the potential response, in the potential outcome framework, we usually have notation for response, potential response variables. This is a variable, and you have to play with independencies between potential responses. And this is really, really not intuitive, and that's the issue why I would say Perl's framework became very popular, because if you read this, no human can understand this, I would say. And in the framework, basically they say, let's assume that this is true. And then, okay, what? But I don't even understand what this means. Like, what is the independence between a counterfactual quantity and a variable, and what is this? That is actually a way to interpret this independence, and it is through a counterfactual graph. I don't want to explain here how to construct, but if you have like this backdoor graph, this is a backdoor graph because Z blocks all the confounding paths between X and Y. And you can construct these counterfactual graphs by putting the parallel graphs, one in the scenario where it's the observational world, then you put together the graph in the world where you perform the intervention, then you collapse the variable Z because Z is the same variable. You don't really need to understand it, but you need to know that this exists. And the lesson here that I want to tell you is that in the potential outcome framework, this is framed as an assumption. And this is not an assumption. You can test it if you have the graph. And then we will see later that you can even learn the graph and do a complete, fully testable way of applying the backdoor adjustment. So if you read papers where it's saying, let's assume ignorability, let's assume conditional ignorability, or conditional exchangeability, or unconfoundedness. They are all saying that the set Z that you have in hand blocks the backdoor paths, all of them. And you just saw examples where scenario where this may not be able to happen. So you need to know that you are under this assumption for applying these tools. That's all, okay? Questions about this? So, of course, there are many other scenarios beyond adjustment. So, for example, we have the front door, we have the conditional front door, we have the napkin, and you see that the formulas are all being different for different graphs. You can have unnamed, you can put your name on this graph if you want, but that's a different formula, you know? And there's no way to deal with this by hand. Of course, you have a calculus. The do calculus, if you have heard, allows you to derive this formula by hand. It's simple. It's just 3 rules that you apply, but you have to play with the probability axioms, and you can derive. The LD algorithm do this for you for free, right? So let's just use it. So that's why I wanted to conclude before we start the code. But as let's summarize here, we have tools for Markovian models. Let's just go back here for Markovian models where you have no observed confounders. We call it G-computation formula. This is basically just applying the truncated factorization, because since you don't have unmeasured confounders, it's all there's always a way to factorize given the parents, and that's all you need. So if you have the parents, it's the same thing, right? You just use the truncated factorization. It's always identifiable. Now if you have unobserved confounders, then the things becomes tricky. You have, for example, backdoor adjustment. There's the generalization of backdoor adjustment that's called generalized adjustment. There's the front door adjustment. There's the do calculus. There's the identification algorithm, and so on. So all of these you can check in Perl's book if you really want to know, right? And this is the thesis of Jin Tian. He developed most of these ideas related to the algorithm there. I would say that like this is one of the best theses I ever read. To be honest, it's like amazing. If you really want to know about the idea algorithm, just read his thesis. It's like amazing. Okay. I just want to give you a few references just for you to know that the field didn't stop in 2002, right? So we have like several advancements in the sense of getting identification, combined observational and experimental data instead of having hard interventions. So I told you that the intervention here, the do x equals to x, is called hard intervention because you just change the x to a constant. You could change the x to another function. So you are doing something that we call soft intervention. Many times you have just a probability of changing the outcome. I would say, for example, some policymaker decide to promote or like to during COVID, for example, it's incentivizing us to use masks. Not because it was incentivized that everyone started using. So this is not a hard intervention. So there's a probability now, probably higher than before, that people started to use masks, but it's not definite. So this is called soft intervention. There's now ways to combine deep neural networks by basically using the causal diagram. So the causal diagram is still the input of it, but it's using this as an inductive bias to force that your model is agreeing with the graph, and then you play with like optimization approach to see if for all the models that fit the causal diagram have the same causal effect, and if you have, then you have the identification. So there are ways to combine, but they're still requiring a causal diagram, right? So it's not just fitting a deep neural network. So let's go to code here. We have in this link below here directly the Google Colab notebook. Let me open mine. So I ask you to first create a copy on your drive. I already have my copy here, so I will just clear all my output and just start again. So the setup here, so first comment, this is really small probably, yeah, that's better. Yeah, first comment here, this is in R, and why R? So there are a few packets starting to develop tools for in Python, but they are still so there are most of the basic tools, I would say. Backdoor probably is there, ID algorithm is there, causal discovery is there. So most of the tools that are basic are there, but if you want something more sophisticated, most of the tools are in R. So I use R, and that's why I'm presenting here ER. Of course, you are free. You have like the do Py, you have PyY, you have do discovery, you have many other packages available. Just search on Google, you see if you prefer Python. But I want to present this in R because once you know at least how to do this, you can at least, so there is a package that's called PCAlg I'm going to install. And you see that there are a lot of packages here that you would have to install. But to speed up here, I basically already have all the packets, the binaries in my GitHub. So this setup here, if you run it, you're going to download my package, and it's going to be hopefully faster. This takes forever to install. That's why we are not doing this. So this is going to take around 5 minutes, or not even, because I already have my packets installed, but in your computer it's going to take a few minutes. So at home, if you on your computer, you would like, and you probably want to install all the packets, so that's why I left here the instructions to install all the packets. But here I'm just making a copy to your environment, and then we are just loading the libraries. Okay, so you see here the PCAlg library is one of the most famous for causal discovery and identification through adjustment. The causal effect is where it's implemented the ID algorithm, so we are going to use these two. And the others are basically just to plot, because the plots from these libraries are like the most horrible graphs I've ever seen. So basically, I implemented my own, so I'm giving you here the code. So these helper functions have, for example, this plot function that I implemented, plus a bunch of other functions to just simulate some modules here for us to play. So let's just run here. So in the first part, I don't know why this is taking so long. Let's ignore this. So in the first part is model definition. So of course you would never define the model here. It's just for us to simulate data. So I'm simulating here. I'm using structural equation modeling. So it's just a model that has linear functions, Gaussian variables, but you would not know this, right? So this is just for us to generate data. And I have here one confounder. So if I plot, so that don't scream as how ugly is this? This is from the package. So you see here that I'm basically, here I'm just computing the diagram. So from the structure causal model, I did by hand how to get the corresponding graph, right? And you see here that there is this UCD is a U variable that's pointing to D and C, so it's an unmeasured, unobserved confounder. I also have this UAB pointing to A and B, and D is pointing to B, and B is pointing to C. If you make like a concise version of this, you would see, let me draw this in the board, because we will use this graph later. So we have here B pointing to C, this as a confounder. This would be the graph, okay? And then A, I believe is like this. This would be the graph using the notation that I explained to you, but this is using iGraph, so it's just for illustration. This would be dashed in our notation. This would be also dashed in our notation. And B is pointing to C, and D is forming this confounder. So if I apply here backdoor adjustment, I want the effect of C given to B. So is there a set here that satisfies the backdoor criterion for the effect of B on C? What would be? You just need to block a confounding path that's between B and C. So we have this path. This is a non-collider. So if I condition on this, I block this confounding path. Okay, it's easy, right? So this would be the adjustment formula for us. So it's like, here is always the probability of the outcome given the treatment and the set Z. Z has only the D variable, and here's always the probability of the set of covariates, so it's just D. Okay, so just for you to know, we will simulate this. So identification via adjustment here. Are you all with me? Yeah, okay. So to do this, we have first, so we use this function here, which is coming from the PC-AUG package. And I'm using here the adjustment, I'm using the adjacency matrix that's coming from the true causal diagram. So this is just converting to an object. It's called MAG, but you don't really need to know this. If you are interested, I can explain what's a MAG for you. But we need to do this conversion before adding this to the function. And then I'm asking here, I want the effect of X on Y, and I want all the possible adjustment sets that I can have. And if I'm printing here, so it's just here. This probability is identifiable via adjustment, and since it is ADJ returns, it's a list of all the adjustments. Since it returns more than one element, we will have that this is identifiable. And the first adjustment set is just the variable D, as I told you. It's also giving me A and D. What do you think about A and D? Can I adjust using A and D? Yeah, right? So basically, if I condition on A and D, I still block all the confounding path. So A is not hurting. So I can use, so that's why I said there's all here. I can also ask for a particular set to see if it's admissible or not. So here it uses the index of my list of labels. So so this is a adjacency matrix. Maybe I can print just for you to know. I don't want to restart because I have to install again. But this is just adjacency matrix. So the number, the columns, if you print your computer, you see that the columns of the adjacency matrix is the labels of my matrix. And I have to use the index of the variables. So I can ask here if the effect of the variable x on y is identifiable through some variables. And in the next cell, you can see that there is this function, GAC, that's the generalized adjustment criterion, that I put the z here as one of the parameters. So I'm asking if the effect of x on y given z is admissible for adjustment. And if it is, I have in this variable here the answer. So the answer for z equals to 1. 1 is my variable, my first variable, which is a, right? So that's I'm printing here. So I'm asking, can I identify the effect of b on c just conditioning on a? And the answer is not, right? So it's not. I'm afraid of restarting here, and let's restart because otherwise I won't be able to play with you. But there are some questions in the yes, good. So there are some questions. Maybe I'll give you a few. Oh, I'll figure out why here. So there are some questions here for you in the end. I want to ask you if the effect, what's the effect of D on C? So now, I want to know if in that graph, what's the effect of D on C? So you see that the effect of D on C is through this path here. So that is a causal path from D to C, but it's confounded here, okay? And I want to see if it's possible. So through adjustment, this is not possible, right? You have a confound. So hopefully the answer is going to be no, but please play. How you do this, you basically replace, so we are here, effect via adjustment. You can ask, what's the effect here? Just change, 2 is the index for B, right? So I want to know what's the effect of D on C. So it's just put 4 here. Let's see if I can get it. Okay, it's not identifiable via adjustment. And then you could ask me, and now what should I do? Should I just give up? We will see that, yes, so I don't want to give up, right? So hopefully there's like some other ways to do it. And that is the ID algorithm. So the next step here is the identification via the ID algorithm. And I can play now again. So if I use y as the C variable and x as the B variable, I would have hopefully the same formula, right? Because the causal effect through so the ID algorithm is complete. So if I run this cell, the marginal effect of B on C is identifiable and is given by this formula. So you see here that the output is exactly the adjustment over D, right? For the effect of B on C, okay? Let's change now C. I want the effect of D on C, right? That's through this other path. Let's see if we get something else. And yes, you see that this is actually the front door adjustment. So the effect of D on C is identifiable through a formula that's not the adjustment. So if you write this, it's like the sum over B of the probability of B given D, and then the sum over D of the probability of C given D and B given multiplied by the probability of D. So it's like a monster. This is like a front door estimation. So this is this formula here. So you see here that this plot, if I move this in the other way around here, you can open like D pointing to B and then C. B is the mediator, and you have this bidirected edge. So the idea algorithm is able to give you any formula that's possible to be computable as long as the effect is identifiable. So the adjustment is great. So many people are still working under only these assumptions. However, the idea algorithm is more powerful, especially if you can construct a causal diagram. Okay? You can also compute conditional causal effects. So you have the Z parameter here. So in my case here, what's the effect of B on C given D? You'll be exactly the observational distribution of C given D and B. Okay? Yeah, so my question now is, what can we do if we have no knowledge to construct the causal diagram? So this is more like, let's play with causal discovery. So questions for the first part? Okay, so let's move. Let's continue here. So what if domain knowledge doesn't allow us to construct a causal diagram? So just to motivate a little bit, the number of graphs that we can construct increases, like is super exponential in the number of nodes, in the number of variables. So just consider the space of DEGs, so no unmeasured confounder, right? There is a recurrence relation that gives you the number of DEGs given for a particular number of nodes n. And here is the table. So if you have two variables, you can play and say, okay, I have two independent variables, one pointing to the other pointing. And I'm considering just DEG, no bidirected edge. With 3, it's 27. So if you start like, okay, let's draw all possibilities by hand. Oh, I have knowledge. Let's try to construct by hand all the possibilities. It's 27. Okay, you can do in one day maybe. 4, 729. 8 is already to the power of 13. So 8 variables is kind of, oh my God, like what can I do, right? And the problem, so basically enumeration is not a good idea, right? And the problem becomes much bigger, the space is much bigger if you consider the bidirected edge. So this is just a comparison. So already with 3 variables, I would not be able to do in one afternoon, I guess. But it's impossible, right? To the power of 21 with 8 variables. So what actually we need then something is smarter than just enumeration, right? So there are algorithms, and the algorithm is going to leverage these inferences that I told you that exists across these modules in the equivalence class. So causal discovery is just basically it assumes, not assumes, it recognizes that many models are statistically indistinguishable without additional parametric or distributional assumptions. So here I'm going to present first an algorithm that's not assuming anything regarding parametric or distributional assumptions. And in this scenario, which is non-parametric, we will learn only. So the class of models is called Markov equivalence class. So it's a class where all the models are encoding that set of the list of conditional dependencies and independencies. Okay, and the algorithm that I'm going to tell you here is the fast causal inference algorithm. Why this one? So this is like this was developed in 2008. It seems old, however, is the first one that actually accounted for latent or unmeasured confounders. So you can learn the class even if you have unmeasured confounders. And most of the methods that are still being developed today are extensions of this one. So even if you like, okay, let's consider something more recent, is not much different than this one. It's just this one plus something more, right? So basically, this is what we have, in my opinion, is what we have best up to today. And what the algorithm does is the following. So we have the same figure here. We have data. We don't know all the multiple models that could generated it. We learn the conditional dependencies and independencies from the data. And here is a case where x is independent of y, and then we have a third variable z, but conditioning on z, we have dependence. Maybe you would remember, this is the case of the collider, right? So this is all models that I could construct it. Of course, the algorithm is not doing enumeration here. It's just playing with a lot of rules. I can explain later more. But in the end, it's going to capture all the invariances that are in this class. So it's going to learn an object that's called partial ancestral graph, and it's going to have that look there. So you see that there is a circle on x and in a circle on y, because there is at least one model in this class where you have either a tail or you have another model with an arrowhead. So this is not an invariance. So you have a circle because both models are there. And you have an arrowhead on z because all of them have the arrowhead. And this is learnable, okay? And it's called ancestral graph because edges here, the meaning of the edges are ancestral relationships. So they are not necessarily direct cause relationships, but ancestral means you have a causal path. In that plot, in that graph there, D is an ancestor of C. So D is a cause of C, but through another variable. But as long as I know that intervening on D, I will see a change on C, I'm happy with this. So I'm not requiring to be direct causes here. So this is kind of the pipeline. So I'm just putting here on the top the true model. You don't know it, but that's our, we imagine that we want a class that includes this model, right? So the algorithm starts with the complete graph. So the complete graph has no assumption encoded in it. This is like the weakest possible model. It's like I can parameterize every model inside of it by just setting some parameters as 0, and then you eliminate some edges. But this is encoding the entire class of models that I can have among these 4 variables. But then it uses some condition independence tests, and here there is a strong assumption that we can discuss later that tells me that I have a condition independence test that tells me correctly all the independencies and dependencies that I have in the data. So this is something that if I have infinite data, I'm sure that it will have faithfulness, but with finite data, I may have problems with this. So a line of research that I've been working a lot on this direction is how to model uncertainty related to this test, so you can incorporate the uncertainty in the causal diagram, in the PEG as well. But this is like in the original algorithm is assumed as like either is correct, like it's definitely correct, so you have like all the dependencies and independencies available for you. But once you have this list, you basically remove all the edges that are related to independency. So you see you remove the edge between x and w because you found some conditional or marginal independence between them. Here, x and y are also not with an edge because you have at least one conditioning set that given this set, they are independent. Then you apply this, there actually the rule 0 and then plus 10 rules. So it's an 11 set of rules that you apply, and then you get in the end an object. And you see here that we learn more than a collider. We actually learned, so first we learned that W is a cause of Y. And this is correct. According to our true graph, this is correct. More than that, I learned that Z is also a cause of Y, but it's green here because we have a property that's called visibility, which means that the Z variable is not confounded with Y. You can basically see some similarities. It's flipped, but that graph there is also part of this class here. Just change the labels as instead of A, B, C, D, is going to be X, Z, Y, W, right? So you can kind of rephrase, relabel there. And that graph is also part of this class. And you see that W, maybe I should write, it's too much for you, I guess. Like, let me rephrase here. So this is like X, Z, Y, and W. And then I want this. Oh, sorry. Yeah, it could be this, doesn't matter. But this is a causal diagram, and this causal diagram is part of this class, and you can see that W in the graph that I draw there is an ancestor of Y, and this is represented by this edge. So this is capturing that W is always an ancestor of Y in every model of this class. And Z is also an ancestor of Y, but in that model, Z cannot have a bidirected edge. So the model where the bidirected edge is between Z and Y is not part of the same class. I can explain if you're interested later. But the model where W and Y are confounded, as is in that case, is part of the same class. If you just list all conditional dependencies and independencies through the separation, you see that you have exactly these two here. And what I'm telling with this is that the visibility property, that's why this is green, tell you not only when is ancestral relationship, when is also, I'm sure that this effect is unconfounded. So there's no way to have a bidirected there. And this is marked with this V, visibility, and those are the edges where I will be able to at least try, is to have like the possibility of not have identifiability for the visibility, the visible edge, but a necessary condition is that the edge is visible. It's the first condition that you have to have for identifiability of the effect. So the effect of W on Y here is not identifiable, but the effect of Z on Y, it is in this case. Yeah, okay, so you have here some description about the edge. You can see that bidirected edges, if I have like a bidirected edge like this, is just spurious association. It also deals with selection bias. So if you have selection bias and associations due to selection bias, is going to be represented by undirected edges and so on. Let me move here. And this is the class, as I told, is a class of causal diagrams. And I'm listing here some causal diagrams that's part of the class. Maybe one of them is that one. Yes, this one, you see? So this one is one example of why the effect of W on Y is not identifiable, because there is a bidirected edge here, although that is an ancestral relationship. Okay? Yeah, so you obviously don't know what's among all these graphs is the true causal diagram, but at least you know that if you have identifiability from the peg, this effect is going to be identifiable through an equation that's going to be valid for all these methods. So it doesn't matter what's the true diagram, you have your effect. This is just some examples where would be the input, like the underlying causal diagram, and the output of the FCI. So if this is a collider, you have just a collider. If it's a fork, you have just circles, but you see that at least there's no edge between X and Y. That's an example where I learned that X is visible, the cause here of X and Y is visible, and you learn this directed edge. You don't really learn about these other relationships. This is another example where you learn that definitely Z and W are just spuriously associated, so as is here, and that's the example we saw. Questions? Are you following? That's the most important part. All right. So condition dependence test is like a building block of this algorithm. So when you are trying to apply this method, you need a way to detect conditional dependencies and independence. There are many tests available in the literature. So the oldest but the most used one is the partial correlation test, where you have just Gaussian variables. So this is like one of the most used ones, but assumes that all the variables are Gaussian, right? So the other one that's also very popular, but it's in the other end of the spectrum is the one that's completely non-parametric, so accepts any type of functions here, and it's called the kernel-based condition dependence test. So the power decreases as you are having like a more general test. So you need more data here if you're trying to have extract accurately conditional dependencies and independencies in a non-parametric way. But if you have a lot of data, I would recommend this one. If you have mixed, and this one also assumes everything continues. So I don't know if they have already an extension for like discrete, but there's no possibility to have mixed data. If you have mixed data, like in your data set, you have binary, ordinal, multinomial, conditional, Gaussian, whatever, you can play with regressions. I'm putting here linear, doesn't necessarily need to be linear, but you can play with like, you can detect conditional dependencies and independencies by comparing regression modules. One paper that explains how to do this is this one. I use this, I think it's the one that I mostly use. Of course, if you have like ways to, if you have to model other things in your data, for example, if you have like non-IID data, you can play with mixed models. So for example, when you have family data, you can model this using random effects. So you can kind of develop other condition dependence tests. So you just need to find what's the best or the most appropriate test given your data set.
Would it work if for non-scalar random variables, so if the random variables are multidimensional, and for instance, they have different dimensions, so x and y?
Yeah, that's a very good question. So doesn't work. Yeah, because if you need to enforce this dependence. So if you have like two high-dimensional variables, you can detect dependencies in pairwise, but not in triplets. Because like imagine like a graph like this. Imagine that you have like V1, V2, V3, and V4. And you have this connected to this connected to this, and this was formed together. So you can kind of have like the correlation between the group and V1, the correlation between V3 and the V4, but the correlation between V1 and V4 is like, that is, there's no connection between V3 and V4, so there's no path connecting. So this graph, you tell you that V1 is independent of V4, but you have like kind of a fork here. So it doesn't work pretty well. Works for independencies, but not for dependencies. You can detect independence. So here, V1 is independent of V4 given the high-dimensional variable. Independence works, but dependencies doesn't work. So for structural learning, you need both. You need to know where is also dependent. So actually, it's a method that I've been working for like a year or more with a student at Columbia University, and we are trying to solve this by imposing some assumptions on top of the high-dimensional variable to make it work, because the general problem is really hard, like we haven't figured out yet. If you're interested, we can join. But yeah, it's a very interesting problem.
Even with the PC algorithm, I think there is a stable version of PC algorithm also.
Oh, this is stable means that the skeleton part is made in a sense that you don't have order dependence. Because and this is because of unfaithfulness. So if it's faithful, doesn't need to be stable, but under unfaithfulness, which is like having some condition dependencies that are false, depending on the order that you start looking for these conditioning sets, you will stop always in the first. And it's possible that you got the wrong one. And then this ends up being very bad in the end. So it's like just a trick that we run this orders like the size of the conditioning set. So we try to find this conditioning sets that makes a pair of variable independent by increasing size by like the conditioning set it starts like with no variable, then one variable, then two variables, and so on. Like it's increasing size of the variable. And this is stable in the sense that it's order independent right now. Yeah.
And how much data, here it is written small sample, but what is like arbitrary small sample?
Yeah, that's terrible. Yeah, yeah. So in the code that in the code that I shared with you, to have like always good estimated pegs, I put 10,000 samples for 4 variables. Yes.
So if you, I mean, it is not something that can be used with certainty when we have less data, maybe like 150.
No. I mean, you can use, so I've been working exactly on this because I've been trying to apply. And one big advantage of the FCI algorithm is that you can handle latent or an observed confounder. So you can always do selection first and see if the effect is identifiable with like 4 variables. If not, you add another one that you have in your data set because you just shrink to make it able to run. And then you can do this in an adaptive way. But it doesn't matter what's the selection of variables you had, you always have to have something that we call marginal consistency. So you can kind of implement some marginal consistency tests or robustness tests to make sure that you are having always the same inferences. Or you can also modeling the uncertainty. So I have a paper that is with Eliezer and people that worked here with the professors Helge and so on from NTNU. We try to model the uncertainty by using a Bayesian approach. So we are learning the distribution of all the models. So under unfaithfulness, the most likely graph, it may not be the true one, but if you move a little bit around the mode there, you see all the alternatives you would have if you had like different outputs, and then you would basically have a Bayesian way of analyzing both the effects and everything. Yeah. Let me converge here. I think I'm almost in the end. So we have extensions. So instead of using a causal diagram, you can run a causal discovery algorithm like the FCI. And for effect identification in this class, we have some extensions. So for example, the backdoor adjustment was extended to have the generalized backdoor adjustment. For covariate adjustment in general, from causal diagrams, we have the generalized adjustment criterion. So this is just the reference for it. And recently, we also extended the do calculus and the ID algorithm to have marginal and conditional causal effects from pegs. So that's the reference. We have now the pipeline where the second input doesn't need to be the causal diagram anymore, is just the peg. So you can put the peg that you just learned from the FCI algorithm. And this is now constructed, the entire pipeline is constructed in a fully data-driven way, right? So if you have identifiability here, you would have, and this doesn't need to be the backdoor, right? So this one is the backdoor adjustment. If you use the generalized adjustment criteria, you would be able to get this effect from the peg, right? So this is a method that was developed in 2018 by Perkovic and others. And through the ID algorithm, we don't need anymore to be a peg where the effect is only identifiable through adjustment, can be identifiable through anything, is a complete algorithm. So this, we have IDP, which is ID from pegs, or CIDP, that's conditional ID for pegs, so it's for marginal and conditional effects. And if you have an answer, then you have like your expression mapping the observational distribution to the interventional distribution you have available. In the code, I have also a way to learn. So you have there a piece of code for learning a peg and then to apply the IDP algorithm. I don't think we'll be able to run this. It's also available in my GitHub if you want the package. So this code that I shared is already installing from my repository. And identifiability from the PEG has the same idea, right? So it's just that the class now is bigger. It's bigger than a causal diagram. The causal diagram is a class of functional models. Here, a PEG is a class of causal diagrams, which is, again, each one is a class of functional models. So it's a bigger class. So in sometimes we have identifiability, so that's the case of the example we have in the code. So this means that doesn't matter what is the effect, what's the causal diagram, we will have always the same formula for every effect. Right? If we have no identifiability, so this would be a non-identifiable effect. This means that at least one of the models, so this is a model that is still part of this class. You can see here because this circle allows anything here happening on X. And this effect is not identifiable on this graph. This means that the entire class cannot have the effect identifiable. So there are many other topics in causal inference. So before concluding, I need to tell you some advanced topics so you can look after if you are interested. So first is like there are some causal discovery that allows cycles. So actually they prove that the same FCI algorithm, that I said, the FCI is not that bad as 2008, it is still being the base of many of the most recent developed algorithms. So they proved that the same FCI, so no change in the algorithm, it recovers the cycles. However, instead of using the M separation is the extension of this separation to pegs, we have a new extension of the M separation, which is called sigma separation. And then you can actually see what are the models with cycles that are represented within the partial ancestral graph, which is the PEG. So we have also causal discovery from time series data. So some people even came here to talk to me what happened with, you have the temporal dimension here. So there are extensions of the FCI algorithm as well for time series data. Basically, you enforce that the present doesn't causes the past. And this is just kind of an arrowhead that is forcing to not, so you have like every point on the past is pointing with an arrowhead to the present and never a tail from the present to the past. And then you have some other tricks, because once you have like this time series data, conditioning on the past becomes a conditional probability with a high dimensional variable, and this has a lot of issues when you infer from data. You also have causal discovery assuming linearity. So if you know that your model is linear, you can do more. So it's more than, so you go beyond the Markov equivalence class. Because I said Markov equivalence class is non-parametric, you only use conditional dependencies and independence. But if you can assume anything more, so for example, linear models, you can do more and your class is going to be smaller, right? And being smaller allows you to identify more effects. You can add prior knowledge. So there are papers where you can basically reduce the class by adding prior knowledge. You can have some models that are called additive noise models. So every function in the structural causal model is now a function plus a noise. So this is additive noise. If you have this type of assumption, you can again go beyond the Markov equivalence class. You can do causal discovery from interventional data. You can have like a data-driven way to select the variable that's admissible for adjustment. So instead of learning a PEG and run the backdoor adjustment on top of the PEG, you can skip the learning the part where you learn the PEG, you are focused only one edge specifically, and then you see in a data-driven way which variables, which set Z satisfies the backdoor adjustment. You have partial effect identification. So sometimes you saw here, no identifiability. There are actually some works that instead of saying no for you, it's going to try to give you a confidence interval, basically, where the effect is going to be. This can be informative or not, but you can try. Fairness and mediation analysis. So this is some techniques that uses counterfactual reasoning. One of the examples is of counterfactual estimation is the individual treatment effect. So if you want individual level effects, there are also methods. Most of these counterfactual techniques are still in the backdoor scenario. So they assume that you are in this scenario. But there are many more. And I put here a lot of papers that I found, in my opinion, are the most interesting right now to related to these extensions, right? So I told you a list of extensions that I'm very interested to read. So for example, those are the papers where they show the foundations of structured causal models with cycles and also under latent variables. So they establish what's a Markov equivalence between cyclic directed graphs. These are the papers related to time series data. They also are characterizing the equivalence class for this scenario. Linear models, prior knowledge, you can check later, and additive models, interventional data, data-driven covariate selection, partial effect identification, mediation analysis, treatment effect. And yeah, so causal representation learning is another one that I put here. I think I forgot to update the list there, but it's something that's very popular right now. Basically, you try to work with high dimensional variables instead of nodes. You have like clusters of nodes, so it's a coarser representation of your graphical model. So there are many extensions on this direction. And those are things that I already mentioned before, but there's also here a new topic, optimal causal experimental design. So in the end, if you have no identifiability, there are also some methods, although most of them are under unconfoundedness assumption, that allows you to know what would be the best action, either observing variables or performing experiments to, in the next iteration of this loop, you have identifiability, because it will be improving the constraints of your model. And causal reinforcement learning, to me, is something very popular that's combining reinforcement learning and using the causal diagram to efficiently do the part of exploration. Yeah, so I don't think we'll have time for the tutorial, but please do at home. It's basically causal discovery and effect identification from PEGs. I hope you enjoyed the lecture. If you have any questions, I'm happy to take now or after, or even through email. Please, thank you. Just